Well, folks, what do you need to know about bonding for the AP exam? Let's go through this as fast as I can. Let's start with the types of bonding. So, when I think about bonding, I think about four things, right? First off, I think about ionic. In an ionic, I have a metal cation that is attracted to a non-metal anion, right? And this is going to form a crystal lattice. Um, Electrons have been transferred at some point, but it's the positive and negative. And of course, I should start off here with bonding is what? A strong electrostatic attraction, right? That's what we're talking about between two things. So this is a strong ionic is a strong electrostatic attraction. It's going to be ruled by Coulomb's law, right? K Q1 Q2 over R squared, and the lattice energy will be, and this has a very high boiling point because it takes a lot of energy to separate the cation from the anion. Next, we usually talk about molecules, right? Molecular bonding. And molecular bonding is a form of covalent, right? Bonding in which we have valence electrons that are shared between nuclei, right? And this forms a molecule. So don't confuse molecules with crystal lattices. And these have low boiling points and melting points because when these things boil, you're just overcoming IM forces. You are not breaking the covalent bond. You're only overcoming the IM forces. Where over here, when you boil or melt an ionic compound, you are actually overcoming the strong force of attraction between the cation and the anion. Another type of bonding that I think of is metallic, right? And what's important to remember about metallic is, number one, it's metals, right? And by the way, my covalent is usually non-metal, right? So metallic is in all metals except for mercury. And you have metal cations, and they are surrounded by a sea of valence electrons, is what they say. So what that means is that the electrons are mobile. They're kind of free floating. They're not really strongly tied to a nucleus. Now that's important because that explains the electrical conductivity, right? The reason metals conduct electricity is because they have these mobile electrons. So when you put an electrical uh, force on them, electromotive force, a potential, an electric potential, it's enough to drive those electrons across the metals and conduct the electricity. This also has high boiling point because it's very strong attraction between in metallic bonding. And then finally, we have covalent networks. And covalent networks are similar to molecules, but in molecules, you only have, a small, relatively small number of atoms. Yeah, I don't know, 50, up to 50, something like that. But when you're starting to talk about covalent networks, you're having hundreds and thousands of atoms covalently bonded. So you'd have, a large number of atoms covalently bonded to each other, right? And these guys form a network or a lattice kind of, right? And these tend to be metalloids are involved in here. So you think about your carbon, graphite and diamond, silicon dioxide, boron nitride. These are all covalent networks, very hard and have very high boiling points as well, or melting points, right? And so all of these three all have very high boiling and melting points. It's hard to say which one is highest. It depends on the situation. So that's the background in bonding. So now let's move on to what's next. Polar bonds. Okay, so if we're talking about polar bonds versus polar bonds versus polar molecules, we are really now talking about just this group right here. We're not focusing on anything else. We're really focusing here. And polar means that you have an uneven electrical distribution. So if we have a bond like an H to an H, right? Those electrons in the middle are evenly shared because each of these hydrogens is pulling on them the exact same amount. And so we'd say this is a non-polar situation. And when we have non-polar bonds, every time we have atoms with the same electronegativity. Now, on the AP exam, just assume that unless they give us electronegativities, they're different unless you have the exact same atom. So if they give you two H's, you know, have the same electronegativity, so it's going to be nonpolar. Whereas if you have H and Cl, the H we know is a 2.1, the Cl is a what? Probably a 3.0. And so those electrons are much closer to the Cl. That means I'd have a dipole. And this dipole leads in the direction of the chlorine, where I have a partial negative on that side and a partial positive on this side. Why? Because those electrons now are closer to the chlorine, and it brings electrical charge closer to the chlorine, okay? So what causes a polar bond? Well, just atoms of different electronegativities, which are pulling on the shared electrons differently. Now, that's different than a polar molecule, because the thing about a polar molecule is I can have polar bonds in a polar molecule, in a non-polar molecule. What makes something a non-polar molecule? So a non-polar molecule, two things. Either it's made up entirely of only non-polar bonds. This is rare. I mean, the only time you really have that is something like maybe in O3, right? Where that would be non-polar because all three bonds are exactly the same. Now they have to be careful. That's kind of, O3 is a funky little thing, so I wouldn't even say that. But this almost never happens. Now, the other situation for nonpolar is if my bond dipoles, that means I have polar bonds, my bond dipoles cancel. And that is the justification. If you have something that is nonpolar as a molecule, you'll say the reason it's nonpolar is not because of symmetry or not because of asymmetry, very simply, or not because of shape. It is because the bond dipoles cancel. Now, what causes the bond dipoles to cancel? This is where shape matters, right? When will I get cancellation? I will get cancellation. My bond dipoles will cancel if I have a symmetric shape and symmetrical atoms around my central atom. So what are my symmetrical shapes? 2O, 3O, 4O, 5O, 6O. The other linear, 2, 3, and then 4, 2. Those are my symmetric shapes. Now, what do I mean by symmetric atoms? So let's say I have something like methane, right? Here's methane. You have 4 identical polar bonds, and they're arranged in a tetrahedral, so they will cancel, and this will be nonpolar. However, if I have 2 chlorides in here, now all of a sudden I don't have the same 4 atoms around, so this thing is polar. Now be careful. This might look as if it would cancel, but remember, this is a 2-dimensional shape. These things are really in a tetrahedral, not a flat arrangement. So these chlorides are not really diametrically opposed, and so that's why that is polar, right? Also, if I have, when do my bond dipoles not cancel? If I have asymmetric shape, and that will be all others listed here. You know, my 2-1, my 2-1, my 3-1, my 2-2, my 4-1, 3-2. How about a 5-1? Those are all going to be symmetric shapes, and so they will be they will be polar. They will not cancel. And why don't they cancel? Because of just the shape does not allow for these vectors to cancel each other. So when I say yes, I'm saying yes cancel, no cancel, right? So these will be polar, these will be non-polar. molecules if they have the same atoms around them. Okay, so that's a little bit on polar versus nonpolar, Lewis structures. Okay, you got to go back and make sure you know your Lewis rules, right? Follow the Lewis rules. Count your valency electrons, right? And then remember, carbon, nitrogen, oxygen, and fluorine almost always end up with 8. Things below that, boron can have 6, beryllium can have 4. Anything above that in the periodic table, though, can have an expanded valence. Doesn't mean you have to, but they can. I would try to use octets if possible, but if I come to a situation where I have more valence electrons than I have in my picture, what do I do with those extra valence electrons? We put them on the central atom and expand the valence. So that's one thing. And remember, you gotta write your complete. Lewis structure to get credit. Don't forget these unshared pairs on your external or on your end atoms, all right? So that's really about all on Lewis. Now, we do get a case where sometimes we can have multiple Lewis structures. So I could have written, I could write carbon dioxide this way, and I could write carbon dioxide this way. Both of these follow all the rules of Lewis, and so on the AP exam, both would be considered acceptable. Now, though, the next question is, which of these would be the dominant structure? That's what they'll ask on the AP exam. And what we're going to use to determine that is formal charge. And formal charge is really not that hard to do. Formal charge, we have to write for every single atom, and that's going to be the number of valence electrons minus all the unshared electrons plus 1/2 of the shared electrons. Now, another way I like to think of this is that this is just going to be my valence electrons minus all my dots and 1 for every line I have. Got it? So if I have a single bond, that's 1. If I have a double bond, that's 2. If I have a triple bond, that's 3. So as long as you draw your Lewis structures with the dots, it's pretty easy. So if I want to go back and calculate formal charge for this first oxygen, what is it? Well, 6 valence electrons, and then I count the dots, 1, 2, 3, 4, and then I count the lines, 1, 2. So that would be 6 minus 6 and 0. Got it? Same thing for my carbon. My carbon is a 4, and I have how many lines? 1, 2, 3, 4. 4 minus 4, that's 0. And then my last oxygen is 6. How many lines? I have 1, 2, and then how many dots? 4. 2 and 4 is 6, so all those equal to 0. Now, if I look at the other side here, this oxygen right here, how many dots do I have? 1, 2, 3, 4, 5, 6. And how many lines? 1, 7. So I have 6 minus 7, that's a minus 1. My carbon here, I have 4 lines, 1, 2, 3, 4, so that means that's 4 minus 4. Remember, my valence is 4, so that's 0. And then for my last one, I have 6 for my valence of oxygen. How many lines do I have? 1, 2, 3. How many dots? 2. So 3 plus 2 is 5, and so that's 1. So I have a minus 1, 0, and a plus 1. So that's what formal charge is all about. Make sure you know this. Formal charge shows up all the time on the AP exam, and it's a piece of cake. You don't want to leave that point hanging. Make sure you understand formal charge. Good. What's after formal charge? Okay, resonance. Do I want to talk about resonance now? Sure, let's talk about resonance. Resonance is, resonance is a case where Lewis structures don't work. And really what it means is that you don't have a single, you don't have a double, and you don't have a triple. You have something in between. You have a 1.5 bond or you have a 1 1/3 bond. Now, how do I recognize that resonance is going to happen? It's a case where I have 3 of the same bonding situations, but I end up with different bonds. So if we look at SO3, when I draw SO3, I have to have a double bond somewhere, right? When I follow my Lewis structures, because SO3 there are 24 electrons, so I have to have 24, and this is the only way I get it. But you look at that and you say, holy cow, why should one SO arrangement have a double bond and the other a single? So you see that, and all of a sudden you start getting suspicious and say, that doesn't make sense. It's more likely that all three oxygens would have the same relationship to the sulfur. And so then that's where we have to consider resonance structure. So then I'm going to rewrite this so that I represent the double bond in each of the three oxygen locations. So here's sulfur, and now this is a single, this is a double, this is a single. Complete your electrons, and then do it one more time, and you have my sulfur here, single, double, single, right? Complete your octets. Good, so that's resonance. And what also follows with resonance is what we call bond order. And I like to think of bond order as your average bond in something like resonance, right? And the way I get it is I'm going to, and it's handy here now, we start getting a little more advanced and thinking about, if I have a single bond, that is a sigma, right? You guys remember that? If I have a double bond, that is a sigma plus 1 pi. And if I have a triple bond, that is a sigma plus 2 pi's, right? Good. So I'm gonna add up the total number of bonds that I have here. And so I have a single, so that's a sigma. I have another single, that's a sigma. And then I have a double, so that's a sigma and a pi. So that means I have 4 bonds. But how many locations do I have? I have 1, 2, I have 3 SO situations. So I have 4 bonds spread over 3 SOs. So my average bond is really 1 1/3, and that's what we mean by bond order, 1 1/3. Now, what's a couple things about resonance. They don't have to tell you, hey, draw a resonance structure. It's pretty simple. They can set you up and say, hey, you have sulfur trioxide, but each SO bond is either the same length or same strength, right? Because if they say they're all the same length and are all the same strength, that means they are the same type of bond, right? And if I have a double and 2 singles, well, that's not the same type of bond. How can I get SO bonds that are all the same? I have to use resonance, and then my bond order would be 1.3. So that's the way they can set you up. Also, be ready for our acetates and formate types of situation where you have a COO negative, right? Well, that's not likely to be the case, right? Really, it makes more sense that you have a resonance structure here that is between these, right? So you would have this kind of resonance. Now, of course, this carbon's bonded to something else, but watch for resonance in terms of acetate or propionate or formate or something like that. One other thing, while we're talking about bond order, let's talk about length and strength, right? Strength, if we're talking about bond strength, then triple bond is stronger than a double bond is stronger than a single bond, if we're talking about the same thing. So what I mean is carbon-carbon triple is stronger than carbon-carbon double, and so forth. I can't really compare, I don't know, a carbon-carbon triple bond to a nitrogen triple bond, right? We'll have to look at Coulomb's law for that. Carbon triple bond to an oxygen double bond. Length. Same thing, it's just the opposite, right? A triple bond is shorter than a double bond is shorter than a single bond. So my 1.3 bond is what? My 1.3 bond is what? Longer than a double, but shorter than a single, and it's stronger than a single, but weaker than a double. Okay, so I think that takes care of resonance and bond order and bond strength. And now let's talk about geometry. So when I'm talking about geometry, we really talk about 2 things. We can talk about electron geometry, and we can talk about molecular geometry. So watch what they're asking for. Now, if we're talking about electron geometry, we only care about electron domains around my central atom. And what is that? So here's my central atom. a double bond is one domain, a single bond is one domain, a triple bond is one domain, a unshared pair is one domain, okay? So when we're looking at electron domains, I can have, usually we go with 2, and I need more space here, don't I? 2 and 3 and 4 and 5 and 6. Oops, I need more space, don't I? 6. 6. Good. And what are my shapes of my electron domains? Well, when it's 2, it's linear. When it's 3, it's trigonoplanar. When it's 4, it's tetrahedral. When it's 5, it's what? Trigonal bipyramidal. And if it's 6, it is octahedral. So those are my electron domain geometries. Only answer this if they ask for electron domain geometries. If they don't, ignore it. Now, my electron domains are really made up of what? Bonding domains, meaning bonds, plus non-bonding domains, meaning unshared pairs, right? So in my linear, I'm going to have 2, 0. In my, when I have 3 electron domains, I can have a 3, 0 or a 2, 1. Tetrahedral, 4, 0, 3, 1, 2, 2. If I have 5 5 electron domains, I can have a 5, 0, 4, 1, 3, 2, and 2, 3. And if I have 6, then I have 6, 0, 5, 1, and 4, 2. Right, y'all? 4, 2. And make sure you understand. Make sure you know the shapes, the molecular shapes. This is linear. This would be what? Trigonoplanar. This would be bent. 4, 0, tetrahedral. 3, 1, trigonal pyramidal, right? 2, 2, bent. 5, 0, trigonal bipyramidal. By the way, I would not abbreviate these on the AP exam. I'd write them out. But I figure you guys really know this, and I'm just reminding you. 4, 1, seesaw. 3, 2, T, 2, 3, linear. 6, 0, octahedral. 5, 1, square pyramidal. And 4, 2, square planar, right? So make sure you know all those. Now, we also are going to need to know something about angles. All right? Now, angle for linear is 180. Angle for trigonoplanar, 120. Angle for tetrahedral, 109.5. Angle for trigonal bipyramidal is 120 and 90. And angle for octahedral is 90, 90. Now, 2 things can affect that. So I have 2 atoms, X and X. And here's my Y, and we'll say I have an X here, right? And we'd say, okay, each of these is 120. But if I change this to a double bond, that means I have a greater electron density, and that with that electron density, it's going to be more repulsive. So it's going to be pushing down. So this angle will go up, and this angle goes down. The other thing that can do that is if I have an unshared pair here. If an unshared pair, that's going to compress this angle, and my 120 goes down. Now, you can't just answer less than 120 on the AP exam because they'll say, well, 5 degrees is less than 120, and so you have to quantify that. Say about 120, or a little less than 120, or slightly less than 120. So let's go up here and land just to refresh your memory. So this would be less than 120, less than 109.5, less than 109.5. This would be less than 120. My T would be less than 90. Linear, octahedral, and that's good enough. If you know those, and I'm not even sure how often they ask this, but just be aware. Now, off of this, there's something very important that happens, which is that we can get our hybridization, right? So remember, if I have a central atom and it has anything more than 1 bond on it, I have to consider not just 1 bond. If it has any more than 1 bond, Yes, anything more than one bond, I have to hybridize it. All right. So if it has two bonds, I have to hybridize it. Now, my hybridization is dependent entirely on my electron domains. So I have electron domains 2, 3, and 4. 2, 3, and 4. All right. And then what is the hybridization? Well, if I have two electron domains, and now here's what you have to understand. You have one s and you have three p orbitals that are valence, and those are the orbitals you're going to hybridize. So I'm going to hybridize 4 orbitals. So how many orbitals will I have after I'm done hybridizing? 4. In the case of sp, only 2 of those will hybridize into sp orbitals. The other 2 will stay as unhybridized p's. If I have 3 bonding domains, then I'm going to have sp2, 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 and 1 unhybridized p, and then 4 sp3, 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 sp3. Now, what's important to understand is my sigma bonds can use hybridized orbitals, right? But my pi bonds need unhybridized p's or unhybridized d's. So you got to understand, if I have something like C double bond O, C double bond O, right here I've got a sigma, right here I have a sigma and a pi, right here I have a sigma and a pi. These pi's cannot use hybridized orbitals. They have to use unhybridized p orbitals. So I cannot have a double bond of a situation where I have sp3s unless I am using d orbitals. And that would happen maybe with sulfate, but they don't usually do that on the AP exam. They're looking at very simple things. By the way, if you look at something like, I don't know, let's look real quickly here at acetic acid, right? A typical question is, how many sigmas and how many pi's do you have in this? Well, every single bond is a sigma. So I have 1, 2, 3, 4, 5, 6. So there's 6 sigmas, and then there's a double, meaning there's a 7 sigma, and there is 1 pi bond, right? So that's really all there is about hybridization. I think we have 2 other things. Holy moly. Bond enthalpies. Yeah, so bond enthalpies. Bond enthalpies is really the energy required to break a bond, essentially. And really the only thing we have to worry about here is you can use bond enthalpies to estimate heat of reaction. So you want to take the sum of your bond enthalpies for every bond broken in a reaction minus the sum of the bond enthalpies of every bond formed in a reaction. And so what you have to do is you have to write your Lewis structure, you have to ID what is breaking, and then you have to just use the math. So I have a nice quick little example here. We have carbon monoxide, and it is reacting with chlorine, and it's going to form, I don't know, it's a ether, isn't it? We're gonna have to say the Pledge of Allegiance here in a second, so I better pause. Okay, so if we have this kind of situation, so you want to identify what is breaking. Well, I have to break this triple bond, and I have to break that single bond. So they give me the bond enthalpies, and they say, hey, this is a 1. By the way, all my bond enthalpies are positive. So this is a 1,072 kilojoules per mole. This is a 422 kilojoules per mole. So those are those that are breaking. What is forming? Well, I'm forming 2 of these carbon-chlorine bonds, right? Well, that means it's 2 times 328. And I'm also forming a oxygen double bond to carbon, which is 799. So if I wanted to approximate my heat of reaction, I'll take 1072 plus 242 minus 2 times my 328 plus 799. And that will give you your approximation to your heat of reaction. And then finally, the last thing, lattice energy. Lattice energy is for my ionic compounds, and it's all about Coulomb's law, right? Coulomb's. And the way to think, remember, Coulomb's is F is equal to K Q1 Q2 over R squared. In the case of lattice energy, Q1 we can think of as our cation charge. 1, positive 1, positive 2, positive 3, or really just 1, 2, or 3. The positive and negative we don't care about. Q2 would be my anion charge. And then R is really my cat atomic radius and my anion atomic radius. And in this case, what we're thinking is smaller size means they get closer, and if they get closer, that means R goes down. So what will increase my force of attraction, which increases my lattice energy? If my cat charge goes up, that increases my lattice energy. If my anion goes up, anion charge, it goes up. If my atomic radii go down, that will lead to an increase in lattice energy. So if we want to compare NaCl and NaF, I think what they'll probably do is give you the values and say, hey, this is 910 kilojoules per mole, and this is 788. And they'll say, okay, explain why. And what you'd say is, hey, this is a positive 1, negative 1, negative. They both have the same Q1, Q2. But F is much smaller. The atomic or the ionic radius of F is much smaller than that of Cl minus, which means R is smaller, which means my Coulombic force of attraction is greater, which means my lattice energy is greater. So that's how you'd explain that. If you had MgCl2, which is 2526, right? You look at this and you say, oh, the chlorines are the same, so they're not going to have any impact on why that lattice energy is so great. But magnesium is a 2 plus, whereas sodium is a 1 plus. So that means my Q1 is bigger. Not only that, magnesium, the ionic radius of Mg2 plus is less than that of Na plus. So that means my R goes down, my Q1 goes up. Both of those lead to an increased Coulombic force of attraction, which leads to an increased lattice energy. Okay, I think that's all you need to know in bonding. Good luck.